Today we are going to talk about the paper 3 of the November 2023 session. This was just a few days ago. And I thought that the paper 3 was the most difficult of the three this time around, but that's the kind of thing that tends to make it interesting. So when you sit down for your reading time, you realize that question 1 wants to go through what happens with this function for various values of a and b. It's going to start by setting a equals 3 as a first example. And then it asks you some questions about what the value of b needs to be in order for the function to have 1, 2, or 3 distinct roots. I think that the first thing that you should do in this kind of situation is to consider the case where b equals 0, even though he gave you no indication that that's going to be an interesting answer. But it's just a choice that simplifies things, because now this is just a very concrete function that you can sketch and do things with, because there isn't a parameter in there, because you've set the parameter equal to 0. Particularly if you're going to use your calculator to sketch, then that b has got to go. But I'm not going to use my calculator for anything, basically, in this question. This is the type of question that I like a lot. It is not a quadratic function or any of the basic types of functions that we most commonly are working with, but it's interesting to see what kind of things we can know about the sketches of these types of functions and what things we should know, because I know that the calculator will sketch everything for us if needed, but it helps to solve the items of the question if you actually know what's going on rather than you're just looking at a picture on a screen. So this is a polynomial. I know quite a lot of things about polynomials. I know that the leading coefficient is 1, which is a positive number, which means that in the end here, the function is going to be going to infinity. It's going to do some things in the middle, but it is an odd degree polynomial. So after it does whatever it's doing, it's going to end up going to negative infinity on the other side. Then I factored out the greatest common factor that I could find. And now that the polynomial is factored, I can see the roots. There is 0 and -3 as roots. But more interesting than that, -3 is appearing only once, and 0 is appearing twice as a root because it's x squared. So you have that same root twice. That is the multiplicity of the root. This one has multiplicity 1, that one has multiplicity 2. Not every polynomial needs to get the multiplicities of all its roots adding up to the degree of the polynomial. This one does. It's 2 plus 1 is 3. But not every polynomial needs to do that, only because sometimes you have complex roots as well. That's not the case. This question is not going to deal with complex numbers. The thing that I'm trying to say is that root with multiplicity 1 is like a straight line. It's a linear function, so it crosses the axis like a line would. But 2 looks like the vertex of a quadratic function. That is the case where the quadratic function only touches the axis once. It used to have 2 roots, and then it came up a little bit. Now it only has 1, but it's actually 2 that are in the same place. So that's why it needs to touch and come back. That behavior that you're used to seeing in the vertex of a quadratic function is the same behavior that this function is going to have here. So it touches the axis and comes back up. Okay, so after thinking about it this way, it's easy to get the first 7 marks of the question, because when b was equal to 0, we see that we have 2 zeros of this function, and then the rest is going to be vertical translation. If you change the value of b, then this function is going to move up and down, and of course the number of x-intercepts is going to change. If b is positive, it's going to move up, and then you're only going to have 1 x-intercept over there. But if b is negative, you start putting this function down, then you're going to start to have 3 distinct roots, 1, 2, 3, until you reach this point here. Then you just have to figure out the coordinates of the point. I'm using calculus, but since they are very round numbers, 2 and 4, I'm pretty sure that if you just ask the graph in the calculator, you're going to be fine. But since the vertical coordinate of that point is 4, that means that in order for the function to have, again, 2 x-intercepts, then the vertical translation needs to be -4. It needs to go down. So that's the complete answer to parts A and B. Part C is the same, but with -3 instead of 3, so you just do the same thing again. And then he asks me to consider the case where we have 3 intercepts and asks me a kind of a very strange question in part D. The answer is that the local maximum is above the axis and the local minimum is below the axis. Like, there is no way that this could be upside down, because if this was above, it would be a maximum instead of a minimum. But the reason why he's asking you this question is to lead you into thinking in a certain way for the next parts of the question. The thing that he wants you to realize is that there is this connection between the number of x-intercepts and being above or below the axis. It's kind of an obvious connection after you think about it, but he's making sure that you do think about it. That's why he's asking you this strange question. Because if both maximum and minimum were above the axis, then it would be the case where you only have one x-intercept, and also if both were below. So that's the direction in which he's going. So he is making sure to get your brain to go in that direction as well. Part E is the 5 marks that you should get no matter what, even if you don't do anything else in this question, because it's just find the coordinates of the critical points. You just take the derivative, set it equal to 0, find the x coordinates, then plug it back into the function and you find the y coordinates. And it's a show that, so I'm not even going to do it because the answer is right here on the paper. So part F begins to ask you to consider a particular case. Both of them are bigger than 0, and then subsequent items are going to get you to consider the other cases. But for this case, he asks you whether the points P and Q are above or below the axis, and then you would say that they are both above, even though that's not what it looks like in my picture, because B is positive in this case. Okay, that's not the same case in the picture. And he also asks which one is a minimum and which one is a maximum. He asks you to do that by using the second derivative test. So that is also very easy, 3 marks for you to get. Just take the second derivative and see which one is bigger than 0 and which one is less than 0, keeping in mind that you're in the case where the parameters are positive. Part G is the same thing for a different case, but the answer is now different. Point P is still going to be above the axis because B is bigger than 0. But for point Q, you need this thing to be bigger than 0 if it is going to be above. So it's sometimes above and sometimes below. He phrases that question as, state the conditions on A and B that determine when Q is below the x-axis. And this state the conditions is a command that sometimes makes people nervous because it is not very concrete, like a find or a show that. But these are conditions, okay? That's the only thing he really wants. And you know it's going to be a simple thing because it's 1 mark. So the conditions for this point to be below the axis is for its y coordinate to be less than 0. That's literally the only thing. And then part H, the last one in the question, does not explicitly say that you should consider the other 2 missing cases, but you should. Why should you do this? And this is why I like paper 3 questions. You do need to get this idea of doing something that was not explicitly asked for. So that's always difficult, right? When you have to have the right idea. But he has been guiding you towards that idea for quite a long time. The actual question is about the conditions on A and B for the function to have 3 x-intercepts. That's not the way he's phrasing the question, but it is. It's what conditions on A and B for us to have 3 x-intercepts. A long time ago, he pointed out to us that 3 x-intercepts means that one of these points is above and the other is below the axis. Now, he's asked us to consider 2 cases, one of which does not work because they are both above, so it doesn't have 3 x-intercepts, and the other one works under certain conditions. So now he wants to know what are all conditions for it to have 3 x-intercepts. Of course, we need to consider the missing cases that we haven't considered yet. And it turns out that this case does not work because both are below, so it does not have 3 x-intercepts. but this one does have one above and one below sometimes. So these are the two cases that work. And now we want to put all of this stuff together into one inequality that will be the conditions under which it has three x-intercepts. Now, this is a show that question, so we know what the answer is. And the thing that we need to point out in order to get to that answer is that this expression here needs to be negative when b is positive, and it needs to be positive when b is negative. So we have two expressions, one of which is this one with a fraction and the other one is just b. We have two expressions, and the thing that we want to say is these two things have the opposite sign. Now, how do we get two things to have the opposite sign? And this is an idea that he did not lead you into, but it's the end of the question, so it's okay. You get two things to have the opposite sign when you multiply one by the other, and the result is negative, because minus times plus is less than zero, and plus times minus is also less than zero. And that's the answer. You just distribute and then multiply both sides by 27, you get the expression that he gave you. Now, there is something that you could still question here, because we do want this and this to have opposite signs, but we also want this and that to have the same sign. So it could have been this times a bigger than 0 instead of this. Now, the only reason why I did this and not that is because it was a show that question and the answer was on the paper. I did not think hard enough about whether there was any other reason why it couldn't be the other one and it had to be this one. I didn't choose to think about this because I would not think about this under time pressure in an exam. Okay, it's 5 marks. We've done enough in this question for 5 marks. We've considered the two other cases that we needed to. We've figured out that we need to put something together by multiplying. That's enough. If that's not enough, it's going to be 1 or 2 marks at the most that we're missing. So that is good enough. Okay, so question 2 on this paper has a kind of a different vibe than question 1. I could simplify by saying that it is a more difficult question, which it's fair to say it is. But I think that it's more than that, because, and you can see that I'm going to start on the end, because this is 9 marks, just this part. And I'm not going to say that this is an easy equation to solve. I would never call this kind of thing easy, but it's safe, familiar territory. Did you study differential equations? Do you know how to solve homogeneous equations? Because that's just a technique. When it's homogeneous, do this thing. If you've studied enough and you are prepared for it, this is familiar territory, so you can totally just do it without understanding the context of what is going on in question 2 of this paper 3. That is why I chose to start here, but I am going to go back and do the rest later, because that, I think, is the different vibe that this question has. The other one, we totally understand what's going on the whole time. It's a cubic polynomial, it's moving up and down, it has some roots, right? We know that's what's going on. This one, as I was solving it, at some points I felt like, okay, I am going to do this thing because this question is telling me to do this thing and I want to get the marks, but I don't really know why he's asking me to do that. And it's fine, you can totally go through your paper 3 like that, you'll get the marks. So part E1 asked you to get to the expression y minus x over y plus x from another expression that he also gives you in the paper by substituting some easy things. So it's 2 marks to substitute things into a formula and get to this. And now it's going to be 9 marks to solve the homogeneous equation. The standard trick to solve homogeneous equation is to consider this kind of substitution here. Then you take the derivative. This, of course, requires the product rule. And now you're just going to substitute these things into that equation. There is a cancellation of x divided by x to be done on the right side. And from here on down, it's just separation of variables. We're going to begin by subtracting u on both sides. Now we're going to put these two things under the same denominator. I'm going to multiply both sides by -1 because this is making me nervous, but you absolutely don't have to. Now let's move things around to separate the variables. This integral is easy, that one not so much, but I want to separate it into two integrals, u over the denominator plus 1 over the denominator, like that. So this is easy, it's just ln x. I'm going to put the plus c here. This one is easy as well because this is just arctangent. And that one is not so difficult. You just do a substitution of v equals u squared plus 1. So nothing individually difficult here, but I kind of think that the idea to split it up is a little bit difficult. I don't think a lot of people think of doing that when they see an integral. They want to do just the whole thing as one function, and I am not really sure how I would have done that in this case, especially after seeing the answer where one part became an arctan and the other part became an ln, so I don't know. And that's pretty much it. We still need to organize it a little bit to get it into the format that he wants. So first I can add ln x on both sides. Of course, I need to substitute back u equals y over x, which was the substitution that I did for the homogeneous. And that's it. So if you came this far and you left there nervous because you know that there is technically a step missing after we do the differential equation, we still sometimes want to isolate y in terms of x. And this looks like a terrible expression to try to do that in. I just hope you didn't waste precious minutes during the exam trying to isolate y in terms of x here, because it's not going to happen. And the good news that I have for you is that there's nothing missing. This is already the 9 marks because he did say to give the answer in the form h of x and y, which is this function of two variables here, equals a constant. He did that because he knows that y cannot be isolated in terms of x here. So continuing in the spirit of let's just do what he's telling us to do without really understanding why he's asking those questions, this limit is the last part of the question for 2 marks, which is very doable as well. He wants us to let alpha go to pi over 2 here, and the problem with that is that the tangent of pi over 2 goes to infinity, right? So it's not a number. You have infinity plus a something here and infinity plus another something here, so it looks like infinity over infinity. Made me think of L'Hopital's rule, but that is not the way to go here because this is, well, I was going to say that it's not a function of alpha, but I don't see why not. It could be considered as a function of alpha, but that's not what he expects us to do for 2 marks, okay? This is not going to involve derivatives at all. This is a different limit technique. I am just going to divide the numerator and the denominator, both of them, by tangent of alpha. This one is going to cancel and just be 1. This one is also going to cancel with this one. And both of these fractions are going to 0 as alpha is going to pi over 2 because they're being divided by something that is going to infinity. So after the fractions go to 0, all that remains is 1 over negative f of xy, which is exactly what he asked you to show. Okay, so let's go back to the beginning of question 2 and see what this question is about. He states that it's about a family of curves that is perpendicular to another family of curves. So I'm going to draw one family in red and another family in green. This is the first pair of families that come to my mind that have this property. Every curve in red is perpendicular to every curve in green because every curve in red is a line with slope 1/2 and every curve in green is a line with slope -2. So they are perpendicular to each other. This is not the first family that he mentioned in the question, by the way. He did not go through this step. I'm just saying this because it's where I thought he was going when the question began. I just want to point out that these are families of functions because they have a parameter. So for each value of b here, you have one of these functions in red, and for each value of a, you have one of the functions in green. That's what a family means. It's not just one function, but it can be one of these functions depending on a parameter. Instead, this is the first family that he chose to go with. Instead of the parameter being the y-intercept, like in my example, his parameter is the slope, but his y-intercept is 0. So he's talking about the family of functions that are lines that go through the origin. Well, just look at it. What should I draw in green? What is a family of curves that are perpendicular to all of these lines? It's circles centered at the origin, right? All of these things become a radius of the circle, and a radius is perpendicular to the circle itself. So this is how you write the family of functions that is circles centered at the origin. The parameter is the radius of the circle. You could put a square here if you want. It doesn't matter. But I am going to call it k instead of r because r feels like radius and then it should be squared. So anyway, have I seen this before as I'm going into this question? Yes, of course I have. I know that this family of lines is always perpendicular to this family of circles. But he is not asking you to just visualize that. He does give you a step-by-step to figure out that this family really does need to be circles. And here is where this question is scaring me a little bit, because part A1 is asking a weirdly stated question. He says, write down an expression for the gradient of the line in terms of x and y. Well, it's not weirdly stated. The line is this, the gradient is m, and you want to write it down in terms of y and x. So that's just dividing both sides by x, and the answer is y over x. So it's not that the question was stated strangely, it's that it is a strange question. We are not often asked to do this. So what's bothering me here is to think of a student getting stuck in this very first mark and then not moving on to the other marks. I hope this didn't happen to you. Because even if you didn't quite understand what he was asking you here, if you can just believe him, you can still move on. And I wrote the words perpendicular gradient here because I didn't just want to write this because that's the answer given in the question. It's a show that. So I have to put the word perpendicular in there somehow because this is why the gradient of the green curves is going to have to be minus x over y because it's perpendicular to the gradient of the red lines, which was y over x. So in this one, you just have to show that you understand that this is about being perpendicular. Well, but the next 2 marks are just a simple differential equation to solve. You can just do that even if you don't understand what's going on in the context of the question. Okay, I'm sorry, I'm gonna stop myself right there because after watching the finished video a couple of times, I realized that I wasn't explaining to you what's going on in the context of the question, and that's pretty much what I wanted to do. So here's the thing, how are we going to get one family of functions to be perpendicular to another family of functions? So we start with one family, which in this case was lines, and the slope of the line was y over x, and although it is a little bit unusual to isolate the slope of the line, that is because the slope is the important thing that we want to focus on because we want slope perpendicular to other slope. And even though m is a constant for this family of lines, it's not necessarily going to be constant for the other family of lines. So slope in a line is just a number, but slope in a curve is something that depends on the coordinates of the point, x and y. So we are going to start from this constant slope for this family, but we are going to refer to it as dy dx as if it was depending on which point we are. And then when we talk about the other family, well, the other family is a curve, but it has a tangent line to have that 90-degree angle with the original family. So these are the two things that need to be perpendicular to each other. This tangent line, which in the case of red is itself, and this other green tangent line. So we know what happens with slopes of perpendicular lines. It's minus 1 over the other, which is why the thing that we want from green is that the slope of its tangent line is minus x over y, because then that is perpendicular to the original red one. But then when we write this down, we realize that it's just a differential equation that can be solved. And by solving this differential equation, which is what I'm about to do in the video, you figure out what the curve needed to be in order to have this property of the slope being perpendicular to the original family that you had. So technically you can do this for any family of curves, but it's going to be easier or more difficult depending on what the differential equation is that you need to solve. For example, the next family of functions that the question is going to consider is this one, but he doesn't ask us to do this in that case. Let's see if we can figure out why. And it's either going to be because it's so difficult that you can't do it as a student, or because it's so easy that it doesn't add anything more to what the question already has. But this is the derivative of that. I'm using implicit differentiation, and I'm going to go through this later on in the video if you keep watching. But let's isolate dy dx. So dy dx for the green curve is going to have to be the thing that is perpendicular to that one. And now we have a differential equation to solve. Here the variables are separated. Let's integrate both sides. Well, that doesn't look like what I wanted it to look like at all. This is not the second family of functions that the question uses as being perpendicular to that one. But you know what? This is also correct. Let me show you a video here. So I guess this is a third reason why they didn't want to ask us to do this, right? Is that if you follow this process, you get a family which is perpendicular, it is correct, but it's not the family that they wanted us to work with. So they didn't ask us to do this, and they just gave us the two families. But I'm getting way ahead of myself here. Let's get back to the video. Well, but the next 2 marks are just a simple differential equation to solve. You can just do that, even if you don't understand what's going on in the context of the question. This one is just separation of variables. And just integrate both sides and organize it to get it in the format that he wants. So now the next thing that he wants you to do is to sketch these two curves. Yet another thing that you can do without having any idea what's going on in the question, and it's going to be 3 marks. Now, what makes me nervous in this question is that I imagine a lot of students will start this by taking the square root on both sides so that they have y in terms of x as a function. And that's not wrong, but there's an easier way, which is to look at x as a function of y and just treat this axis as the independent variable y and this axis as the dependent variable x. Then you're just going to be sketching two parabolas, but you're looking at it like this. I always tell my students that whenever he asks you for a sketch, you need to put all of the relevant features in there, even if he doesn't ask you to. But in this case, he was so specific that he wanted you to mark the x-intercepts and that he didn't want you to mark the intersections. So I'm pretty confident that this is enough. It's weird to me that part C is 6 marks because it's literally just solving this. He wants you to find the points of intersection, this and this. And then you just put one of the curves equal to the other one because y squared is equal to y squared. From this, you get the value of x. Then you put that value of x into the equation of one of the curves and you get the value of y. That's all. And it's also a show that question, so you have this answer as the coordinates of point M in the paper. And part D, the next question, is the interesting one. He wants you to show that this is a right angle. And because this is being done in general for the things with parameters A and B, not just for these two curves, this makes it the second example of two families of curves that are perpendicular to each other. So all that you need to do is to look at the derivative of both functions in that intersection point and make sure that those derivatives are the slopes of perpendicular lines. Now, I'm sure that if you go the long way, taking square roots on both sides to look at that as y as a function of x and then taking the derivative of that complicated function that has a square root of something else inside, I'm sure it works, but I don't want to do that because I want to save time. So I'm just doing implicit differentiation. I'm just doing ddx on both sides, okay? So the derivative of the right side is negative 4a. And for the derivative of the left side, I am using the chain rule. First, the derivative of y squared is 2y, and then I have to remember that there is a dy dx inside of that. Also remember that I'm interested in doing that at this point m, so the y coordinate is 2 square root of ab, and these 2's are going to cancel out. And then if you do the exact same thing to the green curve, you get this as the derivative of the other curve. And well, yeah, these are slopes of perpendicular lines, because if you multiply this by this, you get -1. So now that we've finished going through the questions, I want to show you some illustrations of the examples that he used. This was actually the first example that I showed you, which is pretty obvious. It's lines that are perpendicular to other lines. This is the example with the circles being perpendicular to the lines that go through the origin. And so you can see the right angles that I marked there on the picture. And the black lines are tangent lines to the circles, okay? Because in the software that I'm using, I am not able to plot the angle between curves. I have to plot the angle between lines. So the way that I did that was to put the tangent lines in the pictures. But I also have this other picture where I hid the line, so maybe you can see a little bit better, which is the angle between the red family and the green family. This one is the second example that the question goes through, the two parabolas. And for this one, I chose to make a video instead of putting a lot of red parabolas and a lot of green parabolas. I just have one that can change depending on the parameter. If you notice on the left side, I am changing the value of the parameter, and that changes the picture. But at the point of intersection, you always have that 90-degree angle between the two tangent lines. And finally, this one is the one in the end. The green curve is the very complicated curve that we got as a solution to that homogeneous differential equation. Of course, it looks complicated because it is a complicated equation, but it changes depending on the parameter that we are using. And the red family is, again, circles. He didn't say the word circles in the question, but he did say consider the case where the derivative is x over y. And we had already considered that case earlier in the question, so we know that it's the case of circles. So there you go. You can see that as I change parameter, the green curve changes. As I change the parameter of the circle, which is the radius, I also get larger circles and smaller circles. But whenever there is an intersection, that intersection is at a fixed angle of 45 degrees, which was exactly what the question was asking me to do. So if you are watching this video because you are an IB student that just took this test a few days ago, and if you would like me to talk about the other papers, please let me know. Write a comment in this video saying that this is something that would interest you. Because to be honest, I've been a little bit disappointed with how the YouTube algorithm has been treating my channel. I do have a ton of subscribers, a lot more than I would expect to have gotten within the first year of starting the channel. But most of those subscribers are not IB students. And a lot of them are not even interested in watching videos where I'm speaking English. So I understand that if you just took the IB exams now, it probably doesn't make that much sense for you to subscribe to the channel right now because you're over this. But you probably have younger friends in your school who are still going to go through this next year. So if you could share with them, that would mean a lot to me. Thank you.